IP doesn't have any notion of time, right?
No.
So an IP packet, and even with UDP payload, both don't have any time in it, right? So an IP packet could live for a year, right? But IP and UDP are unreliable. So the core question, there's essentially three things you need to care about for deep space IP networking. And the core one is reliable transport. How do you make sure that the transport behave properly with those considerations of delays?
And the other two?
The other two, so for transition period, and transition in space might be, we'll see, but sometime we will have orbiters or satellites around Moon and Mars that would not necessarily cover everywhere, right? There will not be a constellation like Starlink on the Earth.
So partial coverage, partial visibility.
Right. Therefore, you communicate, for example, from Earth to the satellite, but the satellite cannot reach the asset on the moon surface because the asset is on the other side, right? For example.
Yeah.
So you sometimes will be able to reach the destination, sometimes not. Therefore, you'll see that what do you do? And if the satellite is actually an IP forwarder, a normal IP forwarder, when the destination is unreachable, you just drop the packet, right?
Right.
That's the way we do it.
You're listening to Ping, a podcast by APRICOT discussing all things related to measuring the internet. I'm your host, George Michelson. This time on Ping, I'm talking to Marc Blanchet from Viagenie, which is located in Quebec, Canada. Marc has over 30 years' experience in networking and protocol development in the IETF. He co-founded the IPv6 Forum and has RFCs back to 2003 in internationalization, IPv6, and many aspects of the protocol space. Most recently, he's been exploring the application of Internet protocols to space communications in the TIP-TOP IETF working group. TIP-TOP stands for Taking IP to Other Planets, and it looks at taking the IP stack to the other celestial bodies such as the Moon, the asteroid belt, and other planets. I caught up with Marc at the APRICOT meeting held in Jakarta. He presented at the opening plenary on the behaviours of the IP stack and in particular the QUIC protocol in very long delay channels that you typically find in deep space. Sometimes these communications are mediated by intermediate routing services provided by spacecraft. Marc has been looking at which protocols above the IP level make sense to use in space and how we can tune protocol behaviours around window size and retransmission using a novel testbed which mimics the delay and loss behaviours to the Moon and beyond. Marc, welcome to Ping. Thank you for agreeing to talk to us today.
Happy.
Can you just tell people a little bit about yourself?
Started working on Internet protocols while I was a student at the university.
This was in Quebec?
Yeah, Quebec City. And the department started to buy Sun workstations. We're French speaking, so Unix at that time was not working well with accents. So I started to see if we could use French by email. Then got starting to look where, how an SMTP could work, and we essentially use it because it was passing right away 8-bit. Therefore, was able to pass ISO 8859.1 characters, which means that French was supported. That was when I started being exposed to Unix. And
so this is before the miming codings were invented.
Exactly.
Yeah, so you were sneaking 8-bit unclean payload into SMTP mail.
Yeah, exactly.
Oh, wonderful stuff.
Yeah.
So we're here. Ping is for measurement of the internet, measurement that leverages the internet. And you have spent recent years working in a particular niche of internet technology, the idea of the application of internet to long delay networking, particularly outer space networking.
Mm-hmm.
And you've just presented here at the APRICOT meeting on aspects of applying modern protocols into these incredibly long delay context, which raises a really interesting question. Have you actually got someone doing experiments up there in live orbiting satellites around other planets? Or is this something that we're having to do simulations and modeling on the ground? How are you actually exploring the space?
Good question. I sent my daughter to Mars, and she helped me experiment that.
I thought that was Elon in a car.
No, actually, space is very difficult, right? So, as you could see nowadays, even if we landed on the moon 50 years ago, we're still have difficulty to actually land again on the moon.
The most recent one that I think I saw, they made a remarkably successful semi-soft landing and then the device immediately fell over.
Yeah.
So the opportunities here, windows of opportunity for you to actually get IP active code into space, into, say, a cislunar orbit or even further in space, they are very limited, aren't they?
Well, actually, that one, which was Intuitive Machines lander, and one of the payload was actually the Nokia 4G base station because they wanted to test 3G, 4G on the moon surface.
So there was a deliberate experiment of launching 3G, 4G class band, classic band radio system, standard off-the-shelf equipment, maybe a little space hardened, and there would be more than one active device using cell technology.
Four nodes,
And
so
the layer 1, layer 2 part is kind of designed by 3GPP class specs, 3G, 4G, 4 specs.
There was no special things for space apart from hardening.
So who did the addressing here? Was there like a DHCP server up there?
That I don't know. I haven't, but I don't think it mattered by that much. But so space is hard, right? So you want to, at the same time, simulate a lot as much as you can, right?
Yeah.
Down here, even if you cannot fully replicate the environment. And then, as many have done, which is do this in stepwise, right? You try something and you go further.
So the classic problem here is that space is huge. And we're used to the idea of geosynchronous orbit satellites running IP technology, and that's a delay component, which as users, our personal experience is, well, it's a bad delay for voice. But if you're actually doing directed IP like DirecTV, even geosynchronous orbit is really quite remarkably tolerable in terms of the kind of packet rates you can achieve through it. But that's close to Earth. Moon is a significantly higher delay.
A couple of seconds, one-way delay.
One-way delay of a couple of seconds. So that's a very long time to have things in flight and then discover on arrival you've got corruption. And it feels, this is the naive view, but it feels like those increasing distances are a massive problem for a protocol that has to have reliable packet delivery.
And the last three words are the important ones, right? Because IP doesn't have any notion of time, right?
No.
So an IP packet, and even with UDP payload, both don't have any time in it, right? So an IP packet could live for a year, right? But IP and UDP are unreliable. So the core question, there's essentially three things you need to care about for deep space IP networking. And the core one is reliable transport. How do you make sure that the transport behave properly with those considerations of delay?
And the other two?
The other two, so for transition period, and transition in space might be, we'll see, but sometime we will have orbiters or satellites around Moon and Mars that would not necessarily cover everywhere, right? There will not be a constellation like Starlink on the Earth.
So partial coverage, partial visibility.
Right. Therefore, you communicate, for example, from Earth to the satellite, but the satellite cannot reach the asset on the moon surface because the asset is on the other side, right? For example.
Yeah.
So you sometimes will be able to reach the destination, sometimes not. Therefore, you'll see that what do you do? And if the satellite is actually an IP forwarder, a normal IP forwarder, when the destination is unreachable, you just drop the packet, right?
Right.
That's the the way we do
So
it.
classic IP behavior at this point is wanting to say can't complete, but this is a highly predictable situation. It's not has gone and will never be seen again. It's has gone behind orbit, is coming back in an hour.
Yeah. So the first thing you need to do in deep space for the IP stack to succeed is for forwarders that are seeing intermittence, they need to store packets temporarily. Temporarily meaning not nanoseconds, but
Right. So we're used to
seconds, minutes,
we would
hours.
be used to the idea that in a congested network with routers and switches, there's a certain amount of buffering. And there are aspects we've discussed on ping before, how the behavior of networks ultimately is bound in the size of the buffer and the time window to fill a buffer. But you're talking about a different kind of buffering constraint, and one that isn't measured in quite the same way, because classically you size your buffer to equal the length of time packets live in flight in a fiber or in a length of copper. But we're now talking about packets that potentially are in flight for 30 seconds or 30 minutes or 30 hours.
Yeah.
And so bringing time to the table seems to change the nature of the equation. Is it really the same?
So back to sizing the buffers, at the same time, we found more recently, because of data, Jim Geddes, the buffer bloat problem, right? If you have too large buffer.
Yeah, it's counterproductive.
Right. So you need to kind of queue and do queue management and clear out the old packets and stuff. So what I'm proposing is, I said that to Jim at some point, is buffer bloat on steroids. So the first thing you need to do is to store packets, right? Second is, if you require, and I make the assumption that you do require reliable transport end-to-end.
At the end of this process.
Right, because, typically we're sending multi-hundred millions of dollars of a spacecraft into space, and essentially what it brings you is data back, right?
Yeah.
So if you don't provide reliability, it doesn't make sense to me. But there might be cases where you don't need reliability, therefore you use UDP. So you need reliability, but then the typical transport our transport does the following, which is it handles packet loss, reordering, duplication, flow control, and congestion control.
Yeah.
So all those things are based on some counters, some timers, some counters.
Yeah. And active flow back from the endpoint to say ACK, to adjust window size, to request transmission.
Yeah, all those things.
All of those things are predicated on a complete cycle. You to Mars, Mars to you.
Yes. And but if you think about it, really, there's a bit of so essentially, in a nutshell, you need to adjust timers to the expected RTT of your connections, right?
Yeah. So this is the part where IP itself has no concept of time, but the higher protocol that provides a reliable basis, unfortunately, necessarily brought time to the table. Mm-hmm. You have said, however, if you are in a position to tolerate a certain unreliability because of a one-way flow, UDP is going to be okay as long as we have some mechanism we talk about later maybe to deal with loss and corruption of data. Mm-hmm. But classic behavior that we're seeing these days tends to be TCP-bound behavior. So it's got this end-to-end two-way dialogue going on, and you're saying, let's adjust timers. Let's make timers bigger here.
Yeah, and be efficient. So, and I'll talk about the third thing and then come back. The third thing, so one is store packets when you can't forward. Second, adjust the timers or create a profile of the transport for your use case, which is longer delays. And third is, so when I talk about Internet Protocol, people say, my browser won't work in space. Yeah. So you need applications that are tailored for that environment, right?
So the third thing is application tailored.
Right. So applications, what that means essentially is you need to have a kind of a asynchronous design, right? You send a request and then the thread goes sleeping until you get back the response, right?
Right.
And then the second is if you have, and that's typical, if you have in your application timeouts, we'll adjust them related to the RTT you think it will be happening. Right?
Something modern users might not appreciate is that long, long ago, when Mark and I had more hair and were younger, machines weren't necessarily reliable. And it was actually possible for a computer to be turned off in a hard sense during IP transmission. But it's also possible, if you know what you're doing, to turn that machine back on, set parameters for a TCP session and say, here's your window size, here's your packet count number, here's your current state in the state machine, and just carry on sending packets, and you haven't necessarily broken that TCP session. So we already had, to some extent...
It's a state.
It's just state. If you've kept state, things could work. Yeah. So without sending your daughter in orbit out there to be the other end of an experiment, you obviously need some kind of test rig that allows you to behave as if you had this long delay component, packets in flight, and then you have to be able to somehow simulate the storage component and other aspects of behavior like noise and packet loss. So, Mark, how do you construct a test bed to test the idea?
So, before that, you've been talking about TCP. TCP was essentially not suitable for space, right? The three-way handshake and the fact that if you need security TLS, then you add the TLS with handshake. And the fact that TCP is not good in, mobility, changing, IP addresses and stuff. And it's in the kernel. All this make it, complicated to adapt. One of the things we found when we assessed the capability of IP in space is that 3 years ago was we have a new transport, Quick.
Right.
And Quick, while it was not designed for space, actually has a lot of check mark just because it's a modern transport. One check mark is that to establish the connection is only one RTT, right? And that includes the security of it, TLS in it, right? So only one RTT.
The entire packet of data needed to create a secure session binding is one transfer.
Yeah, one RTT. So what that means is, therefore, in a context where it will take minutes, that is useful too.
Oh, yeah. That's made a huge difference already because it's not a three-way handshake across a multi-minute delay.
Right.
The other aspect of Quick that would immediately say is a good protocol choice is that it uses UDP as its substrate.
Yep.
So where TCP layers directly on IP, Quick layers on UDP.
Quick could have been designed to run directly on IP. I think they chose UDP because, it crosses firewalls easier than if you have a new number as a transport in IP.
So you're not necessarily leveraging any particular aspect of UDP.
Yeah, UDP. I think they chose to run on UDP because that's, having a new transport directly over IP means that everybody in the path would have to, and
so
the
thing here that I still find confusing is that Quick to me has always felt like it's logistically up in what I call the session layer. It is a transport, but it has behaviors that are very similar to the classic network session layer behavior. It has session state and it's agile across variations in transport behavior. I'm not particularly bothered that it's like we're skipping a layer in the stack, but it feels like you've floated up to overcome problems in transport layer.
Yeah, you're right. And for example, we've been, Internet engineering has been trying to handle mobility, right? A device that moves to a different network and change IP addresses, or nowadays you're behind a CGN or something, and out of the blue, you're not changing your external IP address, you just change port numbers, right? So we defined mobile IP. It never
really took off.
And nowadays what we do is we kind of handle this in SDKs and stuff, which is essentially the application layer. But Quick is, what happens with Quick is it handles the mobility at a transport layer. Therefore, IP, you don't need to modify IP, and you don't need to modify the applications, so that's the right layer. And because what makes unique the connection is a connection ID, which is kind of opaque within the quick connection. And that connection ID is the thing that remains. So when one of the node is moving, then they just need to recognize themselves with the same connection ID and you reestablish, right?
And the bootstrapping of end-to-end security that happens in the one RTT exchange, there are aspects of those protocols that require session rekeying, but the fact remains within the lifetime of a session key, that kind of key that you're talking about, the application-specific binding there, you can just use that across this secured session. You don't have to necessarily redo the TLS, do you? You
right.
kind of just get everything coming with you for free.
Well, obviously, there's one RTT to confirm, the connection, and then there's the concept of zero RTT, but is subject to replay attacks. But just to say that Quick is modern and more efficient protocol for transport. So when you were asking about simulation test beds,
how do you actually construct an environment to look
right.
like this network?
So the first thing was to actually choose Quick.
Right.
Another feature of Quick, which is user space, it makes everything simpler because
no kernel hacking required.
Right. And then you could have configured your Quick connection for Moon, and then the other Quick connection for Mars. And so it's very agile for those kinds of environment. Essentially, you can do this with, or 4 ways. One is, you put hardware machines and,
Yeah, I remember people testing high-speed transoceanic fiber by borrowing a reel of 2,000 kilometers of fiber and just simply creating a long delay path out of fiber because it allowed them to do lab-level testing of terabit cards. But that's kind of hard when you want to do it to the moon.
Yeah, and costly and everything. So that's one way. Going from heavy to light, virtual machines, Docker, Linux namespace.
So you're using classic operating system container models that people are familiar with to leverage aspects of their behavior to provide your mechanism for a long delay.
Mm-hmm. So what happens is between the last three I was listing, the VM is the most heavy, Linux namespace is the most light, and we actually did both. And we end up doing VMs at the end. And I was kind of the guy who pushed that because I wanted to be as near as possible to the real environment.
Right. And so a VM, to all intents, looks like an isolated operating state.
Yeah, it's an operating system because, sometimes Docker, with networking, and we're kind of,
they do weird cut-throughs.
Right. And I didn't want to have additional concerns about the actual simulation environment just because, we're tweaking networking.
I think I can mentally see where you might go with this, because when you consider VM environments, what they have to do is they have to put a synthetic construct in between the VM and the real networking hardware and logic of the machine. So most of the hosts which implement this provide a number of facilities to create synthetic networks in the machine and then expose them out into the world. Mm-hmm. So are you adding a layer of behavior at one of these synthetic network bindings to provide this massive delay and buffering behavior? Is that how you do this?
Right. So you construct so that over time our simulation environment has moved. We did essentially 2 things. One is where we, as I said, Quick is really the core thing to simulate and optimize. And
you're delivering an outcome that works in Quick.
And so when we started at the beginning, we had kind of a couple of VMs, and you had delays. You use NetM, Linux NetM, TC NetM, which provides delays, packet loss. You can simulate everything. Interesting part is you start, you kind of prudent. So you start with, let's say, delay at 30 seconds.
Yeah. How far do you get on 30 seconds at light speed in space? Where does that take you to?
Well, so, 4 minutes when the 2 planets are near together, Earth and Mars, it's 4 minutes one-way delay.
So you're
it's
an eighth of the way to Mars.
Yeah.
You're talking to a craft traveling to Mars,
for example.
and it's got an eighth of the way there. You're looking at a 30-second delay.
Right. So, and then you do this, and then, okay, well, let's try 60 seconds. And then, it works too. You configure the quick properly. And then at 300 seconds, 5 minutes, and NetM refuses to actually input the 300 second in the CLI, right? It's like,
wow.
You can't. So, you reach the code, it's kind of code,
Oh, no. We don't criticize people who provide software we depend on, Mark.
Let's say I was not able to find easily a fix. I was expecting, just, somewhere to change, maximum range, a limit or something. But anyway, so I contacted the maintainer and told him, I'm trying. And the maximum delay by converging was 272 seconds. And that was on the CLI. And then actually, like in less than a week, he fixed it, sent me a patch, and then he put 2 to the 64 as the maximum in terms of seconds.
Wow.
Therefore, that means you could simulate, many galaxies away.
So
almost the universe.
So we have managed to put devices that are sending some level of signal into the Oort cloud kind of distance. We're a little beyond that in the model. And so I would think that this means the higher the delay, the more buffer you in principle have to hold because of the potential for packets to be in flight. I mean, we're essentially talking about a stream of photons at radio frequency energy moving out from a transmitter, either in space back to Earth or from a ground station heading out towards Mars. And literally, it's a giant hosepipe container filled with photons that are simply going to take this incredible length of time to arrive.
Okay, but that's nothing to do with IP.
That's the lower layer.
They have the same problem today, right?
Yeah.
So when it sent me the patch asking for, testing it, okay, let's say 5 minutes. Okay, works. 1 hour? Works.
And this is full flight test all the way to quick.
Quick.
Coming to a valid completion of data transfer.
Actually, HTTP over quick. So I was sending a GET request.
Yes.
And then the other peer was sending back the response, which was a file. And then I said, okay, 24 hours. Well, at that time, 18 hours was the time to reach Voyager.
Right.
So I tried, let's try to send an HTTP request to Voyager in simulation. And it worked. It just took
so in effect,
2 RTT, which is...
You use some tool. It doesn't wget curl, something that can intuit a quick URL, and you point it into from a VM to a VM with an intervening system that is using a long delay buffer, and you go and have a coffee, or maybe do your washing, sleep, you come back to the lab,
right,
and you have received the file.
72 hours to get the data back. But that's exactly the same problem that JPL has when it communicates to Voyager, right? It sends something and then you receive the data,
So current technology for deep space probes isn't currently using IP framing for their data.
There's no network in space currently.
So the framing that I understand they use is very, very carefully designed error-correcting codes and also replication of data. So they might do something deck tape used to do, and they might send the same command sequence 3 times so that you can do a 2 out of 3 weighted sum and those kinds of things. Yeah. But you can also do reconstruction of the data flow because you have massive overhead of error correcting, which is time expensive if you're talking about terrestrial networks. But if the delay component is measured in minutes or hours, it's worth investing the time, right?
Right. Yeah. So the link layer is actually is a standard by the equivalent of IETF for space, which is the CCSDS, Consultative Committee for Space Data Systems. And so they do codecs in pipelines, so 2 codec in a pipeline way.
Yeah.
And the reason for this is that when they send commands to the rover or to Voyager, you don't want the command to arrive with errors.
No.
So
there's no command received is one thing, but a command that's wrong is a disaster.
It could be a disaster.
Yeah.
Therefore, which is surprising because in normal thinking, people would say, space is hard, therefore the signal to noise ratio is probably bad.
Yes, I was expecting this.
Right, and then given that the power diminished to the square of the distance, when you talk to a Voyager, it's far away, right? So the power remaining at the end is pretty low, and all what I just said is right, but with what they do with error correction, the output of this is when you talk to mission, and I talk to mission operations for NASA, for European Space Agency, they both told me exactly the same thing. I was asking them, not at the bit level, but at the frame level. So after
all of the error correcting capabilities of layer 1, layer 2.
What is your frame error rate?
Yeah.
Say 0. We're not looking at this. Maybe you have seen on TV or you have or on pictures. You have the big mission control systems and a lot of screens and stuff. There's none that has frame error rate, which you and me or a typical person would say.
Whereas the 3GPP class service that you were talking about that was sent up to the moon, that's actually operating in a much more terrestrial error rate. That's a protocol because the delays are short, that it's okay to have loss in the system because you can afford to perform the recovery.
Right.
We're talking here with a very, very long delay. You really badly don't want that. So the framing, the link layer, aims to be as error-free as possible, and it's only that the higher protocols, be they quick or whatever, need some way to say okay, or to emit the stream of data that you're expecting to receive back.
Right, so you should not count on the fact that the frame error rate is 0, but what it says is you don't need to design the system with a lot of packet loss, right?
Right.
So that makes, your considerations for design differently.
So were you able to model the idea of the intermediary system? Because some of the stuff that I believe you've worked on in delay-tolerant networking is deliberately designing things that look much more like old-fashioned, old-school UUCP, store and forward. Were you able to model that kind of behavior?
So, what we did is I said, 3 things to make it work. One is storing packets, when there's no communication window with the destination, profile quick, and applications. So back to, for example, the simple test of HTTP GET. You profile quick. HTTP doesn't have any notion of time, so that's kind of no-brainer. The remaining is a storage of IP. So what we did was a prototype. I had one of my guys who has been doing, kernel kind of thing for the networking stack. And I asked him about, what do you think about, this IP storage, packet storage? Like, shouldn't be a big difficult thing. Did it in a week and came back a few hundred, like 500 lines of C code and done. Obviously like a prototype, but still working very well. So what you do essentially is you use a TON interface on Linux, which is a kind of essentially a virtual interface.
Yeah, which breaks out into user space no matter where the packets come from. You then have a stream of bytes, just as if you were on the network wire, but it's in a program.
Yeah. And then therefore you essentially configure filtering that all input packets coming to the node. You just tell to send it to the TON interface. And then the TON interface, it does very simple thing, which is, okay, you couldn't make it smart or not smart. We decided to make it not smart, which is what you do is essentially say, okay, I received the packet in the user process. And then what I do is I just send it back to the kernel, please forward it. And the kernel, if it is not able to forward it, that's because the destination route is not there, it tells you that. And then therefore, okay, there's no destination route, so store it,
Store it. don't reject it.
Right.
Right. So it changes behavior, but it doesn't actually alter the end-to-end protocol semantics. It's like a naughty, non-compliant intermediate router that doesn't do what most people expect.
Well, I'm not sure it's not compliant, but...
Okay, maybe that's the wrong word.
Right.
But if the normal behavior is when destination unreachable drop, this thing is when destination unreachable store.
Yeah. And then, therefore, what you do is then register to Netlink events that tells you when, for example, you could, register when interfaces are going up or a route are inserted in the forwarding table, one or the other. And then what you do, as I said, I wanted something not smart. Whenever that kind of event happens, you just take your queue of packets and then just try to send it back to the kernel. And if it doesn't forward, then you store it again.
So if you think about the reality of a system in space, you have these radio links and their layer 2 construct is this highly reliable encoding of data, but they also have effectively sideband information, control channel information like signal to noise ratio or loss of signal. So a thing in space is going to say, well, it's been occluded by the planet. I have loss of signal. You sit there and you say, fine. And you wait for the orbital delay. And then you get a signal that says signal reestablished, bit error rate dropping, frame rate rising. We have link. And you then say link, bingo, and you send out the packet stream.
Right. Because on the IP stack, the event that you see is essentially an interface up, right? That's realization.
How it exposes.
Right, exactly. So everything behind, quote, you don't care. Therefore, we didn't do anything smart, but you could make it smarter, right? For example, we did more like a FIFO approach where when a link is back, we just take all the packets in a FIFO approach and then try to forward them. You could classify them based on various, criteria. You could have, and that's fundamental core issue, research issue is if you are aware of, because when the satellite goes, this is all planned and known, right?
Yeah, orbital mechanics are really well understood.
And not only orbital mechanics, but the actual time where the communication window between the peers could happen. If you have that knowledge, you could be smarter, right? Because then you know who you would be talking to and things like that.
You can construct packet trains that arrive to the size of the buffering capacity, sit there, and at the point you get resumption and you're draining, you can be backfilling in the knowledge you've emptied the buffer and it's capable of receiving the next incoming stream and handling it. And so you can kind of optimize the packet flow through this thing.
Yeah, and then you know that in 5 seconds or in 1 second, that communication window will go down. Therefore, you could do smart stuff. Yeah. So, but we haven't done. So with that, we could create the simulation environment. And nowadays it evolved with a UI. And then you create a JSON file which describes the topology, the nodes. And then another file with the nodes and the links. The links include characteristics such as delay, and then all the things you want to simulate, packet loss or, whatever, reordering, all the NetM, and essentially, push to NetM, do this for me, please.
This isn't magic, and there are going to be pathological cases which cause a lot of extra delay to recover from the behaviors. It's not that anything is free here. The point is, subject to tolerance for delay, you appear to be saying the protocol survives. The time-independent aspect of this protocol, it's quite easy now to demonstrate really, really long delays, beyond foreseeable science experiments in space. So radiation-hardened CPUs tend to lag current CPUs by a couple of decades. But nonetheless, we are talking MIPS class.
That's no more the case.
That's not the case anymore.
No, that's something unrelated to the whole discussion we have. But the space agencies have been... So what happens is they used to procure specialized hardware, right?
Yeah.
Arden for radiation. And
wider tracks, all of these things.
All those things. But then they got into a problem. It costs an arm and a leg. A single board could cost you $1 million. So
Right.
it's like, And moreover, it actually doesn't guarantee much because this is done almost manually. Therefore, even if you test one, the next one may not be
Right.
working because it's kind of a manual or almost manual stuff. So in fact, you're trying to have something very, very good, but it doesn't, happen.
So in fact, we don't have to worry about the capability of a space-bound CPU to perform complex error correcting, to run modern protocols, to have enough local cache to run the stack. It's just, it'll run a VM. It's going to work.
All right. And so nowadays they use essentially off-the-shelf stuff that is premium, and then what they do is essentially test them in the lab with all the radiation that they could.
Right.
And then when one CPU or board is not behaving, just, throw it away or actually use it for your other stuff. And then you keep the one that works. So even that, for example, one of the orbiters around Mars was sent in the early 2000s. All the orbiters around Mars are now used as relays, communication relays.
Right.
But
they have an ancillary function.
Yeah, which was essentially observation of Mars, right? They were taking pictures at various wavelengths of Mars.
But they can act as a relay for the on-Mars ground-based surveying devices and provide a higher bandwidth link locally. And then they have space-bound antennas and can be doing signaling on the long path to Earth.
Exactly. So they repurpose them or add that functionality. But then for some, they essentially don't do any more observation. So what happens is for the purpose of observation, because those orbiters were going around the Mars, therefore they could not send data back to Earth because it was not possible.
Yeah,
they had storage, right? So the early 2000 orbiters have like 160 gig of storage, because of you want to store images, right? Which take some. So as a communication relay, you have quote unquote free 160 gig for something that was, designed in 90s.
Nothing in space is free, but for the context of experiments with doing DTN, delay-tolerant networks, layered IP experiments, quick with long delay, the technology that is viable for space, you also know is viable for a potential future IP platform.
Well, I'm not sure we will actually run IP. We could, but my point is it's easy to actually have good storage in space, especially with off-the-shelf stuff and solid-state memory and stuff like that. However, you can't be dumb in a sense that there is no point of sending a 4K video from Moon to Earth, full bandwidth, if what will happen is which would require a lot of storage very fast. Therefore, you would orchestrate applications and network so that you use the overall infrastructure somewhat optimized, right?
Yeah.
If you're dumb, you'll just fill out the buffers, and then when the buffer is full...
There's a time for being dumb, but if you know exactly what you're doing, you will send lower bandwidth state to maintain context and up the bandwidth and the encoding when it's interesting and turn it back down again.
So therefore, in some ways, you want to have big buffers to avoid, packet loss as a standard IP forwarder, which is no destination, drop the packet. You want to avoid that. Therefore, you need buffers. But at the same time, you don't want to use them so much that they will always be full, right? So you need to, it's for adults.
So, Marc, having shown with simulation and earthbound test beds that you actually can have highly delay-tolerant behavior in a quick-based protocol, do you have vision of maybe something in the foreseeable future when we're going to be doing tests in space, perhaps in low orbit or in lunar context? Is that coming up?
Yeah. So we're working with Spanish Research Institute that has a satellite, a LEO satellite right now, and we're working together and using it for the purpose of testing. that would exercise the intermittence because there's only one satellite. Therefore, we'll not be able to communicate all the time. It's not a constellation. But the delay will be LEO delay, right? So that won't test the...
But it tests part of the model, and it also tests in space. It's not an Earthbound experiment. So that's your first level test.
Yeah. The other test that will happen is more as partners of the space agencies that want contracts for the communication relays for Moon.
Yeah.
That's the next step in real space and for Moon. One thing that is, interesting also is that for the European Space Agency, the orbiter name is called Lunar Pathfinder. And that one, they decided to be a layer 2 forwarder. So what that means is we'll act like a switch.
Right.
From the point of view of IP, right? So therefore, they will do store and forward, but at layer 2, which means that device may not need like a switch unless you manage it by IP, may not need to run any IP stack, right?
Right.
It's just at the layer 2.
But if there was an opportunity to test the field test activity, targeting lunar bases, which are foreseeable science experiments, and then potentially permanently occupied space, I mean, that's a long way out. These things become interesting.
Yeah, but even if it's layer 2, you would be able to test end-to-end using IPQuick, but that device, intermittent device, will just not do IP packet storage, but layer 2 frame storage.
Right, so different mechanism, but a similar outcome.
But the same overall. The only difference there is that the forwarder is less smart because it doesn't have knowledge of, you cannot do IP route, doesn't have a notion of IP routes and stuff and alternate path. And so it's, layer 2. So, but that's fine. I was trying to say that you could have different deployment models and still the overall architecture works. Yeah. The other thing that is actually done is that there's a current orbiter that China has sent over around the moon, and they put a quick stack on it. And they actually started to, like last year, have a test with that orbiter.
So there are other research groups looking at this
right now.
This area.
Yeah.
Oh, that's really great. Yeah, Thank you, Marc. That's fascinating. Can people read about this at the Viagenie site?
Yeah, somewhat. We do have, I think, 2 resources. So there's now, since a few months now, a bit more than a few months, there's a new working group in the IETF called TIPTA, means taking IP to other planets. So that's where we do, the standardization, which is at the moment not new protocols. We're actually defining how you would run the IP stack.
It's profiles rather than inventing new things.
Exactly.
We'll make sure there are links to that in the blog.
Before the working group, as I said, we did a lot of simulations and assessments, and we look at NTP, the behavior. Time synchronization is very important in space, but it's very difficult.
Yeah.
So we look at, streaming and all kind of stuff. And so what we did, we had multiple IETF where we were having informal meetings. And so what we're ending into is we have a whole set of slide decks, simulation tools that we open source. All this is on GitHub.
Right.
And the organization is called Deep Space IP. So single word, deepspaceip.github or github.com/spaceip.
We'll make sure a link to that is
and
on
then
the
you
blog
have
as well.
everything we have done there, and we continue publishing the stuff there.
That's really great, Marc. Thank you very much.
Sure, my pleasure.
If you've got a story or research to share here on Ping, why not get in contact by email to ping@apnic.net or via the APNIC social media channels. Also remember the Measurement at apnic.net mailing list on Orbit is there to discuss and share relevant collaborative opportunities, grants and funding opportunities, jobs and graduate placings, or to seek feedback from the community on your own measurement projects. Be sure to check out the APNIC website for all your resource and community needs. Until next time.